Okay, in this video, we're going to talk about heat and temperature. Now, if you haven't already seen these two videos, I highly recommend going and checking them out first because they lay a good groundwork for what we're going to see in this video. These are both from a channel called Veritasium, and in the misconceptions about temperature video, they show how it can be tough to actually judge how hot or cold something is because what we feel is how fast or slow heat is leaving our body. For instance, when you hold a piece of metal, it conducts heat very well, not just electricity. So it's going to seem like it is quite a bit cooler, even if it is just room temperature, compared to something else of the same temperature, like a paper book, as it is more quickly drawing the heat away from your hand. So it may seem like it's actually colder when it is not. We are generally not the greatest at sensing absolute temperature because of this fact, as well as the fact that we are essentially heat engines. We eat food and process it, we burn it essentially, and then we move and do things and we let off excess heat. Our internal body temperature runs pretty high, almost 100 degrees Fahrenheit. So everything else around us is usually pretty relatively cool temperature wise. So we can also just use a thermometer to tell how hot or cold something is, but it doesn't really answer the question of what it means to be hot or cold. We think of it as like, hot stuff burns you and cold stuff is really cold. Then it doesn't really go much farther than that. Like, what does it mean? What is the difference between matter that is hot and what is cold? When I have water and I get it very, very cold and it freezes into ice, or I get it really, really hot and it boils into steam, what's the main difference? When we talk about physical and chemical changes, melting and freezing and boiling and condensing are all physical changes. There's no chemical difference between water, whether it's a solid or liquid or a gas. So the states of matter video talks about that. What the main difference is how the particles move and how close to each other they are. Okay, when particles are moving faster, okay, they have more energy. Specifically, they have more kinetic energy, the energy of motion. All right, and how fast they move relates to how hot they are. Hot or cold being a relative, way of determining the temperature. So really, when we measure temperature, we're measuring how fast or slow those particles are going, or better yet, the average kinetic energy of those particles as they run into each other and bam, 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 smash into each other. That's where we get transfers of heat. Okay, so we're going to dig down into those kind of two things, the scientific definitions of heat and temperature. So what I've got here is two sets of particles. On the left, we've got some higher temperature stuff. All right, and we can see that they're moving a little bit more than the lower temperature stuff on the right. So we might kind of feel this difference as the left side being a little bit warmer and the left side or the right side being a little bit cooler. But on the particle level, the only really difference here is that the atoms are moving around more rapidly on the left side. Okay, a higher temperature means more kinetic energy among those particles. All right. Now, as we continue to increase the kinetic energy of particles, they don't just move faster, they also tend to move out into a larger volume. They tend to spread out more. Since they have more energy, they can now move farther apart from each other. They aren't so stuck together and attracted to each other. So as temperature climbs, not only do particles move faster as their kinetic energy increases, but also they tend to spread out a little bit more and occupy more space. The reverse can also be true. If we were cooling things down, we tend to condense them into a smaller and smaller space. All right. Now this is just kind of a demonstration of a 3D version of this. So as the particles get hotter, they not only move faster, but also spread out a little bit. They move more violently and can escape each other a little bit more. And as they cool back, they kind of slow down. They kind of recondense into that nice orderly structure. Let it go through one more time. It cools down and slows down. So whenever we go from a solid to a liquid or a liquid to a gas, typically it's because of the temperature change. And all that really means is how fast they go and how far apart they go. From a solid to a liquid, like from the yellow to the red, we're going to increase the kinetic energy of those particles enough so that they can kind of break away from each other a little bit and start moving around more. They roll and rotate and move past each other. In a gas, they have enough energy to totally break away from each other and start flying around. And have a whole bunch of distance between each other. if we go the other way and remove energy, we can go back from a gas to a liquid, and then a liquid back to a solid, okay, where they steadily have less and less kinetic energy. You may also notice that the gas down here in the bottom right is a great example of why we take the average kinetic energy of these particles for the temperature, not just the kinetic energy of a couple very select particles. Not only is it ridiculous to try and look at a couple particles at a time because they're so small, but also they're not all moving at the same speed. They don't all have the same kinetic energy. You'll notice that some of these are going kind of slow, okay, whereas others are kind of booking it. Right? And as they run into each other, they also change kinetic energy there too. They exchange that energy as they whack each other, which can lead us kind of into the discussion of heat coming up here. So if we have temperature defined to be the average kinetic energy of the particles, heat is essentially the transfer of that kinetic energy as the particles whack into each other. Okay, so comparing these two, the metal rod and the glass rod, as they're both heated up by a flame, okay, we see the particles kind of turning more and more red as they get, so-called hotter. Okay, but really what we see that as is the particles moving faster. Now, how do they make other particles next to them faster? Well, they run into those particles, and so that moves them a little bit faster even on top of that, and then more and more and more. So all these collisions transfer that kinetic energy from one particle to another, which makes those other particles move faster. So heat is essentially just that transfer of energy from fast particles to slow particles. On the macroscopic scale, what we see and feel, kind of the big scale, the people scale, heat is kind of seen as always flowing from hot to cold. Okay, well, if hot stuff is just fast particles and cold stuff is just slower particles, then we are transferring energy from faster particles to slower particles, higher kinetic energy particles to lower kinetic energy particles, and therefore from hot stuff to cold stuff. Okay, to kind of summarize this, heat is that energy transferred from one substance to another. We always see it move in the direction from hot stuff to cold stuff. Okay, in other words, from fast particles to slow particles. We will never hold an ice cube in our hands and all of a sudden our hand starts to get hotter and the ice cube starts to get colder. We're always going to see it as the ice cube starts to get warmer and our hand starts to get colder. Okay, that's not just some fundamental, oh, we just decided it so it's that way. Hopefully it makes some sense. As those particles bounce into each other, the faster moving ones are going to give away some of that energy as they collide with the slower moving particles. Okay, so energy always moves from hot to cold, from fast particles to slow particles. And temperature is that resulting measure of average kinetic energy of those particles. Okay, again, whereas our hotness is described as faster particles, our coldness is described as slower particles. So do we, when we feel something, decide, oh, okay, this is a bunch of fast particles. I can feel all those fast little particles. And do we use a thermometer to say, oh, this is sensing a bunch of slow particles? Not really. We do say hot and cold relatively, and we say this is warming up or cooling down. But when it comes down to it, this is what's happening at the atomic level. This is what it means for something to get hotter or colder, okay? To absorb heat or to release heat, to be at a specific temperature. It all has to do with the average kinetic energy of those particles and how they transfer that energy from one to the other as they bash into each other.